Hello everyone, and welcome again to next episode of the IFT ZK Call. Today topic is FHE and Snark. And yeah, Marvin, stage is yours.
All right. So, as Igor mentioned, we will be discussing FHE and Snarks. The goal of this talk is for a high level view of it, but we may have discussions that go much deeper. Depends. But the goal is to get a general idea of kind of these structures with the hope of not scaring anybody. All right. So, if you've been in the space for any time, you've seen FHE, you've seen Snarks, and sometimes they're buzzwords that are not explained. So we're going to briefly explain again at a high level view what each of these are. So FHE, it's fully homomorphic encryptions. It's a relatively young field for cryptography. The first realization of it was in 2009, but it's worth mentioning that fully homomorphic encryptions wasn't a new idea in 2009. It was just the first time someone had found a way to do it. I think there was mentions of it in the 70s where people were trying to figure out in the 70s because encryption schemes like RSA, I believe, is um, partially homomorphic encryption, and the difference between partial and full is you get two arithmetic operations with full multiplication and addition. With partial, you only have one. So I believe in previous calls we've talked about like Pedersen commitments. Those are of course partial, where the exponents add together. If you're not familiar with that, then ignore everything I said. But the key is what we mean by allow for arithmetic operations is that we can perform arithmetic operations on the data in a meaningful manner. Okay, so obviously, if I have ciphertext, I can multiply ciphertext, and for any encryption scheme, the question is it meaningful? And what meaningful means is that if I perform the same operations on the message, the plain text message, it will be the same as if I had done the operations on the encrypted message and then decrypted it. That's the key. So F here is just some arithmetic function, again, using addition and multiplication. All right. Okay, so what's the downsides of fully homomorphic? It sounds wonderful. Well, first of all, it doesn't provide any computational integrity guarantees. Basically, FHE researchers, as far as I can tell from talking to one of my friends that specialize in it, they don't contemplate that the server that you're sending your encrypted data to perform a computation is malicious. They just assume that, okay, we're going to apply the function F, and it's definitely F. So the server's doing what it claims. They, of course, worry that the server could decrypt the message, but they aren't worried about the server doing something different than using F, using a different function like G. The other thing I will mention, didn't put on the slides since this is a technical aspect of it, but if I don't mention it, people will think that fully homomorphic encryptions are all amazing. And I mean, they are, but additions tend to be free, but with fully homomorphic, you tend to have an error. Well, you always have an error term, and that error term usually gets a lot worse with multiplication. So you have to do a very costly operation called bootstrapping that kind of reorientates that error term down. Okay, so All right, so that's what fully homomorphic is. Snarks, the much cooler object of the day, only because I like snarks more. Okay, so a snark is a succinct, non-interactive argument of knowledge. So the first bullet point, I think, is kind of true, but take that with a grain of salt. I attempted to figure this out because I never actually thought about when the first snark appeared. So I actually tried using AI to check this, and the first thing it told me was Grot 16, and we all know Grot 16 should not be the first snark. And I got it to give me a few things from about 2010, and that really does kind of look like when snark was first appearing in the literature, maybe 09. Not much earlier. ZK proofs, of course, in argument of knowledge existed since the 80s, but that succinctness, I think, basically started becoming a concern with blockchains. So that lines up with my understanding of the development. So that makes sense to me. Okay. Succinct. Okay, it's a short proof, fast verification. Short proofs because we usually want to post this on a blockchain. Fast verification because gas fees and verifying that it's correct. But what does short proof and fast verification mean? It depends on who you ask. It's the paper that we're kind of basing this on. I'll give you the ePrint number in the forum post because I don't remember off the top of my head. It goes with Thaller's definition, and Thaller's definition is that succinct would refer to sublinear proof sizes and and verification time. Sublinear in terms of the proving time in the statement. But Muhammad might be saying they're going, no, it should be a polylog. So there's a little bit of a argument on what succinct is, but I think sublinear makes the most sense. But anyway, non-interactive. The key here is that when you generate the proof, you don't need to have any communication, as well as when you verify it. You just need to have the proof given to you. This is usually done with fiat shamir heuristics, and I believe a couple of IFT calls ago, we actually talked about some issues with fiat shamir when misapplied. Argument of knowledge, basically just you're claiming you have some knowledge, and this is the proof that that knowledge is valid. So that's the buzzwords. Usually, a snark is proving a given arithmetic circuit. Now, you could have a universal snark that could generate a proof for any arithmetic circuit, but it's still proving the proof. The snark proof I give you is still for a given arithmetic circuit. So, but there's some special cases that you could bicker about, going like if it's a range proof, well, it's baked into the proof, the system, so it's still arithmetic circuit. And usually you probably see snarks paired with zero knowledge. The reason it's usually paired with zero knowledge is because you can get zero knowledge essentially for free by adding some blinding elements. So that's why you usually see it paired. All right, so what are the downsides of snarks? Well, for our purposes, they're quite rigid. If you want to get very pedantic, you could also go, most snarks are not necessarily post-quantum secure. There's been a lot more developments towards that, towards some LAS-based snarks that are relatively new, as well as a lot of the FRI ones. But I mean, FRI's been around for a while, but they've been using it more with Snarks lately. Anyway, so because you have fully homomorphic encryptions and Snarks running around as buzzwords, and just research questions in general, the natural idea is let's shove them together and see what happens, because Snarks, while rigid, should provide that computational integrity that we were saying was lacking from fully homomorphic. Because we want to guarantee that the function that we're applying to my encrypted data that the server's applying is in fact correct. So for the purposes of blockchains, let's imagine that we have a encrypted data, say UTXO, and we want to do a particular transaction via the smart contract, but we send it to a node, but we don't trust a node, and we want to guarantee that they do the prescribed computation. So, obviously with this, you're giving them the arithmetic circuit, but you're going to send that value essentially. You would like to have assurances that this was that they actually used this function. So that's kind of the idea. Not the best explained example ever, but it's there. Okay. There's two ways we can combine it. We can do Snarks applied directly to the FHE operations. And what that means is the arithmetic circuits can be based on the desired computation that is performed directly onto the encrypted data. And this is going to, of course, assert that the claim computation was done correctly and honestly. That's key. And then we could also do the Snarks essentially first, and then do FHE to some extent. So we generate a Snark on the claimed encrypted value. So the way you can kind of view these differently is that we're going to, for Snark FHE, we do Snarks first with the FHE operations, and with this, we are going to do, we kind of separate the FHE out a little bit and do the Snark first. And the second way is going to be using commitments, if you're kind of wondering how you maintain privacy. So this is partially going to be, the Snark proof is going to essentially work with the plain text, which is why you need to use, of course, commitments. Just high level. Okay. So you have two ways that you can combine these. Which one's better? Well, first off, FHE Snark is going to be the more efficient one. It turns out that if you do Snark FHE, it's going to take 29 hours to do a circuit with 2 to the 20 gates. But if you do FHE Snark, it apparently takes 20 minutes. The Snark FHE version is from this paper, and the FHE Snark is from the implementation that I neglected to write down. The paper is actually just called Snark FHE versus FHE Snark, but we'll get the ePrint code to you later. So, but 29 hours versus 20 minutes, that is a ridiculous difference in time. Why the heck do we have it? Okay, there's a message, I think. I heard a ding.
Yeah, just wanted to quickly ask. It is because, like, due to the time of proof computation, right?
It's not just the proof computation. It's actually the ridiculous time difference is because you're doing the snark proof in both of these. The difference is, what are you performing the snark proof on? And that's the crucial difference, because snarks and FHE uses different algebraic structures. Specifically, FHE uses two different, one for plain text, one for ciphertext. The plain text is you could use finite fields or integer rings. That, if you're, finite fields, that's what, snarks work on. FHE ciphertext usually is this weird cyclotonic ring, which is a polynomial ring modded out by a prime number, usually I don't know why it's a prime number, it's power 2, I think. I'm now second guessing myself, so I'll move on from that. But it's a weird structure comparatively. And snarks, though, work with prime fields, and usually smaller prime fields, 128 bits. But if you're in the domain of snarks and you say, I'm working with a small prime, they really mean 64 bits or even 32 bits. So FHE ciphertext is significantly larger, and that's the difference, is that to do the snark FHE, and you're applying the snark to the ciphertext directly, you're having to do a lot of weird magic, essentially, to handle those objects. And that's the big problem. That's where all the cost is. So what FHE, a snark FHE, can't speak. What FHE snark does is it essentially tries to avoid this structural mismatch by essentially applying either to the plain text, which, of course, the prover is the server, and you don't want to give your plain text data to the server. So it's not quite working with the plain text, but it's working with a commitment to the plain text, which is perfectly fine, because most of the snarks are, deal with kind of bilinear pairings or, other nice structures where that plain text field element is in the exponent of a group element. So the snark can work with that. And that's why FHE is going to be so much faster. So that's all I prepared to avoid things being too technical. But I will mention that the FHE snark versus snark FHE has a really cool polynomial commitment that can work with openings for where some of the parameters are encrypted. So that's really nifty and could be useful for another project. But if there's interest, we can, potentially talk about that by itself. I just wanted to keep this talk as friendly as possible. Anyway, other questions, since that's, like I said, all the slides I have.
Yeah. Sorry.
Please go.
Okay. Yeah, thanks for the presentation. Actually, like FHE snark was something new to me, and I was trying to scratch my head to understand this. However, I was familiar with the snark FHE from the ZK and Aztec network. I would like to a little bit understand it more. My question is like, what I understood is like snark FHE is more like applied to the, data that can be private or unencrypted. What I understood, FHE snark is like, it is more like operates on the encrypted data. And as far as I understood, it's more like homomorphic operations and proof generation. I would like to understand like how FHE snark is applied in the practical applications, because I don't know any of them at the moment.
I'm not sure anybody applies it yet, just because this paper, I believe, is from 2025. So I'm not sure it's actually been applied yet. But the FHE Snark could essentially replace where Snark FHE is used. And while I said that it kind of works with more the it matches better with the plain text, that doesn't mean you give the server the plain text. You can use the standard commitments, which are friendly. Well, you can use traditional commitments that are going to be friendly to protecting your data with hiding properties. But what you're essentially doing is I'm hoping I don't misspeak. You're for Snark, for FHE Snark, instead of what you're doing is, as the user, you're going to send the encrypted data along with some commitments to your original data, I believe. This way, the server can go ahead and perform the computations on the encrypted data as they normally would, and then use your commitments to, along with the value, to do some manipulations to the commitments to show that they're essentially the same. That's my rough understanding at the moment. But the application that you would use this in is going to be something where you need to have the validity of where you don't trust essentially the server. So where you need to do a particular computation on your encrypted data, but you don't trust that third party. And that's the big thing. In terms of what kind of computations, they're talking about 2 to the 20 gates. You could kind of view this maybe as like a smart contract potentially as your function in I'm trying to think of an example potentially for Nomos particularly, but you could kind of view it, I would imagine, as a smart contract, as your arithmetic function performing an operation on a token that you want to keep private. So you don't really, since you don't know the node, you can't trust the node, and you want to make sure that they actually do the computation you claim, especially if this is going to be added to a block. So if you're dealing with your encrypted data that's going to be computed and then processed to a block, and you don't get to essentially have the intermediate, you kind of need to have that proof that that's correct. Obviously, the proof in this instance would go to maybe a sequencer. Alternatively, I can't imagine even clients using a 20-minute computation, but maybe you personally run this computation and you want to send it to a sequencer to make canonical in a block. They need assurances that you're not just making stuff up as well, if that makes any sense.
Yeah, it absolutely makes sense. It's a little bit, too technical for the time being, but I will keep digging. Thanks for clarification.
Like I said, it's really any computation where you need to offload it, and you need to be able to have a proof that's correct. So in terms of offloading it, it could be you sending it to the sequencer and the sequencer needing to verify it before making it valid, or you're sending it to a more powerful server, and they're doing these computations. 20 minutes is still absurd. I've heard about a project that wants to get this down to a couple of seconds. No idea how that's going, but 20 minutes is certainly better than 29 hours at least. All right. I think Uger had a question.
Another question, the actual question, but it's coincidence with the previous example. And for the private execution environments, the privacy is actually achieved by the user computes the ZK in their local. So, but since the constrained devices users is really hard, and maybe FHE plus ZK is used for creating the ZK proof with the delegated provers.
Yes.
By with the without sharing the secret witness. I guess for example, more detailed example can be, for example, you want to compute a SHA something and you don't want to reveal it, and you just encrypt it with FHE and then send this encrypted value to the prover. And prover, once the prover applies the SHA function inside of ZK, and then if you get this ZK and you take the ZK proof and you also show that you decrypt your encryption at first, and you will be having the your SHA evaluation without revealing. It's like shortly, it's like the privacy preserving delegation, because in nowadays it's just done by the NPC. It means that the user needs to slice into some pieces to send the different prover, and the prover, each prover conduct calculation individually and then send back again. And of course, it's much more applicable, but it doesn't provide the fully privacy, according to me, because eventually you just share. If there is some collusion between the individual provers, it might be something. But of course, this drawback of the scenario, I think the efficiency so far, but it's getting very fast. So yeah, maybe one of the use cases can be the privacy preserving ZK proof delegation.
Absolutely. For light users, if you got this down to under a second, that would be phenomenal. Because right now, the gas fees would be ridiculous for even. I don't know what a realistic circuit size off the top of my head would be. I know for SHA, in your example, it might be absurd. Mohammed might actually know the circuit size roughly for that, but for something like Poseidon 1 or 2, those are more circuit friendly, and that might be better. I don't remember the magnitudes of those circuits myself. Not trying to put you on the spot, Mohammed. I just know that might be on top of your head.
And he is gone actually.
So fair enough.
Cannot respond.
Oh well, so it's definitely we're going to assume he knew it right off the top of his head and had important meetings to attend to. Other questions.
I think there's no more question. So yeah, then we can wrap up. Thank you, Marvin, for the session, and see you in the next episodes.
All right. Bye.